To understand how motors operate, we're going to start by looking at a current loop in a uniform magnetic field. We'll see that the current loop cannot translate, but it can rotate. So we have a current I flowing around our current loop. So every current element IDL will experience a force IDL cross B. So integrating IDL cross B around the current loop will tell us how much force the current loop is experiencing. Since I is constant, we can move it to the left of the integral. We can change the order of the cross product, which introduces a minus sign. We are dealing with a uniform magnetic field, so we can move it to the left of the integral. So this is the resulting equation we have for the force on our current loop. Turns out that this integration is equal to 0. There is a difference between the integral of the vector dl and the integral of the length dl. So the magnitude of dl is equal to rho d phi, and to go all the way around our circle, we will integrate from 0 to 2 pi. So everywhere on our circle, rho has the same value, so we can move it to the left of the integral. So this integral will give us 2 pi rho, the circumference of our circle. This integral is the vector sum of all these dl's all the way around our circle. So we'll start at 0 and integrate all the way to 2 pi. So let's think about the situation when we've integrated part of the way around. So the vector sum of all these vectors will be the following vector. So now let's continue and add some more dl's. So when we've gotten to this point on the circle, our vector sum of all these dl's will be the following vector. So let's continue to add our dl's. So when we've gotten to this point, the vector sum of all these dl's will be this vector. And you can see as we continue to add the rest of the dl's all the way around that in the end, the vector sum of all these vectors will be 0. So the force on a current loop in a uniform magnetic field will be 0. So the current loop will not translate, but it can experience a torque and rotate. Here we have a rectangular current loop, and it's constrained to rotate only along this dashed line here. Part B here is looking along the axis of rotation. So the axis of rotation is this point right here. The current flowing at you from D to A is this point right here, and the current flowing away from you along B to C is this point right here. So this rectangular current loop is represented by this wire I have here, and so this dashed line, that axis of rotation, allows this current loop to only rotate like this. R1 is this lever arm, so this lever arm here will be minus R1, and the magnitude of R1 will be half the width of our rectangle, or W over 2. Let's compute this force on the segment going from D to A. So the force is going to equal the integral of I dl cross B from D to A, which will be from 0 to L. The current is constant, so we can move it to the left of the integral. If we change the order of the cross product, we'll get a minus sign. The magnetic flux density field is constant. We can move it to the left of the integral. And the integral from 0 to L of dl will just be the vector L, whose length is L and whose direction is the direction of the current flowing from D to A. Finally, let's switch the order of the cross product, so we'll end up with IL cross B as the force on the line segment from D to A. And the force on the line segment from C to B will have the same magnitude, but will be in the opposite direction. So let me add a minus sign here to indicate that. So now let's compute the torque on our rectangular current loop. So the torque will be lever arm R1 crossed into F sub 0, and lever arm minus R1 crossed into minus F sub 0. The torque then is 2 R1 cross F sub 0, and now let's substitute what we found earlier for F sub 0, IL cross B. Now R1 and L are at right angles. So the cross product will be the magnitude of L times the magnitude of R sub 1 times the sine of 90 degrees, which is 1. So here is the result for R1 cross L, and this unit vector A sub n you obtain using the right-hand rule. You put the fingers of your right hand in the direction of the current flow around the current loop, and your right thumb then points in the direction of A sub n, which is a unit normal to the rectangular current loop. So let's substitute this expression in here in our torque equation for R1 cross L. So we get 2 times our current I. For R1 cross L, we get R1L and the unit vector A sub n crossed with B. Now, for the magnitude of R sub 1, we're going to substitute in W over 2. So these 2's will cancel, and we're left with I times W times L, our unit vector, crossed into B. Now W times L is just the area of our rectangular current loop, so let's replace W times L with S. So here is our expression for the torque on our current loop. We are going to define this term as the magnetic dipole moment, and we'll give it the symbol lowercase m, and since it's a product of a current and an area, the units for magnetic dipole moment are amps meters squared. So if you have a current loop in a magnetic field, that current loop will experience a torque whenever the magnetic dipole moment is not pointing in the direction of the magnetic flux density field. If you put the fingers of your right hand in the direction of the current flowing around this rectangular loop, your right thumb would point in the direction of this vector A sub n here. So that would be the direction of the magnetic dipole moment. So for this position, this loop would have a torque on it. And so this loop would be rotating in the direction of the arrows I've just drawn here and here. So when this rectangular current loop has rotated to this position, we see A sub n is pointing in the same direction as B, so the cross product between the magnetic dipole moment and the magnetic flux density field will be 0. And the torque has gone to 0 on our rectangular current loop. To turn this into a motor, you would add a commutator, which is a rotary switch that periodically reverses the current between the rotor and the external circuit. And the rotor is just the non-stationary part of the motor. It would be the rectangular loop in this example. Here is a website that has some animations which will greatly help in visualizing how a motor operates. Here are some screenshots at different points in the animation. So let's start in the upper left. So the current is flowing around the rectangular loop as shown. So putting your right fingers in the direction of this current flow, your right thumb points in the direction of this arrow here, so that's the direction of the magnetic dipole moment. The magnetic flux density field will go from this north pole to this south pole. So the current loop will experience a torque and will want to rotate like this. So this next screenshot is after it has rotated a little bit. So there's still a torque and it'll still keep rotating. And when it has rotated to this position, if there was still a current flowing, there would not be a torque because the magnetic dipole moment would be in the same direction as the magnetic flux density. But at this point, the commutator comes into play, and you see that the electrical connection is broken between the battery and the current loop, so the current will quit flowing, but because of angular momentum, the loop will keep rotating, and then the connection will be reestablished, but now with the current flowing in the opposite direction. The magnetic dipole moment had been pointing in this direction. Then when the connection was broken, so no current was flowing, there was no longer a magnetic dipole moment. When the connection was reestablished, the current is now flowing in the opposite direction, so the direction of the magnetic dipole moment has flipped from pointing up to now pointing down. And so now again there's a torque on the loop and it continues to rotate. The next two videos are going to be demonstrations of simple motors. Let's first explain the operation of analog meters using the torque equals M cross B. If we have a current flowing in our meter, it's going around this square loop like this, resulting in a magnetic dipole moment pointing upwards. The magnetic flux density field in this region between these two magnets will point from the north pole of the magnet on the left to the south pole of the magnet on the right. So when there's a current flowing, there will be a torque on this square current loop. But as it rotates, there's a counter torque due to this tension spring here. The larger the current is flowing in the meter, the larger will be the magnetic dipole moment, which will result in a larger M cross B torque. The needle will rotate more before the M cross B torque is balanced by the torque coming from the spring. This is how an analog meter operates.